this is something of an overview of much of the work that I've been doing with my collaborators. I'm very fortunate to have many, many collaborators, both in academia and in industry. So I'd like to acknowledge them there. And as I always say, everything that I say that you find interesting is a group effort. If I say something silly, I did it all by myself. Okay, so what are some of the things that people are worried about when we're looking at cloud systems, and in particular, your activity on the internet? Well, one of the things, of course, that people are worried about is, for instance, hiding where you're going, right? And we are all familiar with the Tor project. Some of this work was actually sponsored by a DARPA project that is actually the backer for Tor. But you know, we were actually the only non-Tor project, the only network coding project. But as you know, even after what happened, for instance, you know, it's a perfect place to talk about it, in London with the Silk Road conviction, some people are not that sure about Tor, okay, because there is a lot of trust that's expressed there. But it's not always exactly clear whether they're back doors or not. Some people believe they might be. People would, of course, like to do things like posting, anonymous posting. So I'm sure many of you are familiar with this. This comes out of Pastebin. Pastebin, as we know, probably is a convenient snippet sharing service that continues to be very actively used to make makeshift anonymous broadcast mediums. So it's perfect, for instance, if you just want to send a piece of code. It's anonymous. As far as we know, really, it is anonymous. And that's why Anonymous uses it. But you know, how can we sort of have the benefits of having something like Pastebin, which is anonymous, but having something like Tor, which will allow you to get whatever content you want, not on a one-time flash it on the screen, capture it sense, but really streaming and much more diverse content. So the way that most of the work that we do in the group, at least in distribution, is very much based on random linear network coding, which is work that came out of my group. And the idea is the following. So we all know that normally to transmit data, we break it into pieces, which are generally packets, but might be chunks, for instance, if you're doing a download of other content. The pieces then are needed to be reconstructed, and then you, of course, need the specific pieces, okay? So, for instance, if I get 2 blue pieces, that doesn't make up for the orange piece. And what we're doing in random linear network coding is we're taking these pieces, and we'll see in a minute what I mean by this sort of patchwork that we're creating here. We're going to be combining them algebraically. There really should be a mix of colors, but then they would all be just brown, and they wouldn't look very distinct from each other. So bear in mind for the artist's rendition here of algebraic mixtures over some large Galois field. And in that case, basically what you have is whatever mixtures you have. If you needed 5 pieces to reconstruct, any old 5 pieces will do. So as I said, how do I do this? Well, generally I'm considering packets as vectors of numbers, generally binary or any number. Binary generally doesn't do it, by the way. You really need to go over a larger field. And then you're going to be taking linear combinations, where by linear combination I mean that I'm ponderating by some coefficient all of the elements in the vector. So imagine this packet 1 here is just a vector of elements over, say, GF2 to the 8. We tend to use to GF2 to the 8, but there are other things that we use sometimes. And this is not a compression of that. That's 4 packets. It's also 4 packets with now a little header to take the coefficients here, 1, 7, 4, 3, 2, 8, 9, 5, and so on. This should be a 4. And basically, you take these coefficients, and you append them, prepend them, put them somewhere in the packet. And the only thing that's different between those and these is that these are more flexible. So why do I care? Well, let's give you some idea. Suppose that I have a multi-path, multi-cloud system. So here I have one cloud, multi-path, and another cloud. So it's both multi-path and multi-cloud. What happens if I'm missing some packets because, for instance, I have a failure that occurs, say, on this link, so the link is red, it's failing, then I need to figure out how to get those specific 2 pieces. I can try to get them from here, or I can make a new request to get it from there. Or I could just be using random linear network coding, sending it along merrily, and I'm just getting pieces here. I get 3 coded pieces, and in this case, even though this cloud is coding and this cloud is not coding, what I see is that I'm able to get 5 pieces by combining what's coming from this cloud and what's coming from that cloud. Okay, so I don't have to do the sort of catching up that's so difficult to do, which is one of the reasons why multipath TCP, for instance, which is basically in more or less a fixed form right now at AETF, although people are still tinkering with it. That's why it's so difficult. I don't have to deal with it right now, right? I just get whatever I need, and of course this is looking very rateless. Okay, so basically what it's doing is it's really enabling packet networks. I no longer have to, in effect, just stick packets on top of some routes. I'm really getting that the packets are running all over, and the packets are being obtained, in particular from different clouds, and I don't need to have onerous and generally impractical coordination. So what do I have? I can take this to the next level up, have a coded mesh, distributed storage, and this is one of the things that is unique to random network coding, as opposed to having to do something like, say, a fountain code, where I code at the source, decode at the destination. I can re-encode on the fly. So I can have packets that are sent from one location and then coded and then re-encoded. These could be coming from different locations. And I can indefinitely recode with as much depth as they may be in the network. So this way, I can be completely adaptive. I can be mobile. I don't need to decode. I don't need to coordinate. I just take packets. And by the way, this is very different from flooding, because I'm not repeating the same thing over and over again. I'm just sending as many equations, as many degrees of freedom as are needed. And once I don't need any more equations, I stop. OK. So let's go back to my question before. I'd like to have the benefit of Tor while having the plausible deniability of something like pastebin. So here's one I show, for instance, how you could use network coding, random network coding in that way. I have different users here denoted by their different, which is shown by their different colors. I'm going to have unicast data submissions, and then I'm going to mix them all up here. And what I'm going to do is I'm going to have a plausible deniable local decoding, where I basically just end up having to look at whatever was the key of each of these guys. And just because you're listening to this pool mixer where everybody's been mixed, it doesn't mean that anybody can figure out whether you're listening to Alice, Bob, Jack, or Jill. Now, if Alice, Bob, Jack, and Jill are all troublemakers, then you know that you're listening to troublemaker. But this can be, of course, mixed in with all sorts of innocuous type of data. So you're basically emulating a broadcast medium while providing confidentiality and enabling plausible deniability in terms of reception of content. You can also do secure distributed storage. So it could also be that you're trying to distribute your data, but you actually don't trust any one of the providers. And we'll see this a little bit more later. So then what can happen is, remember those coded blocks, those little different colors? I can put different coded blocks in different locations. And by putting those different coded blocks in different locations, and we'll see a little bit more of that later, I can... OK. Is that me? No, it's all right. Somebody's trying to find their way or updating the software. It's OK. So basically, what's going to happen here is that anybody who has just one of these blocks cannot decode. As a matter of fact, you can show very strong security properties of these different coded blocks, because what you're doing is you're using some of the data in the file to act as a one-time pad to other data in the file. Okay, and of course, one-time pads are perfectly secure. Of course, these might not be one-time pads entirely, because there's some issues around distribution, which I'll get back to later in the talk. Okay, so basically, what you're allowed to do here is have an untrusted storage, and just have one part of the trusted storage. For instance, keep just say 10% of the file that's not available over these untrusted clouds, and in this way, you're able to recover the data that you wanted by doing this kind of decoding. All right. So one of the things that also is making clouds stormy, as you know, is that how do we keep the clouds safe? How much does keeping the data, for instance, inside borders help? Of course, there's been a lot of legislation in Europe, which I'm sure you're more familiar with than I am, in order to keep the data inside borders. This has issues. It has cost issues. It has flexibility issues. And one of the questions is, could I actually have untrusted storage, particularly outside my borders, but just manage the untrusted storage, a little bit like I said before. So let me give you an idea. Suppose that I don't trust any of these guys, or maybe I do, but I'm just being cautious. And I'm keeping my data. I have accounts on these 4 systems. Well, one of the reasons that I might actually want to even use all of these is actually to do some speed up. Let me show you why this counts. So for instance, I had the 4 clouds. Suppose that I do coding over the 4 clouds. What you see here on the abscissa is the time of processing, milliseconds, until I get my entire file. And here are the different clouds. So what you can see is cloud A starts quickly, and then it comes in fast and furious. Cloud B starts second most quick. However, it's very slow after that in delivering. Cloud C is faster than Cloud B, but starts later. And Cloud D is just kind of very anemic. Basically, at this point, I have enough degrees of freedom. I have enough coded pieces to decode. So I shout bingo, and I decode. Okay, that's really what a rateless code does. What you can see here is that I might be wanting to code across each different clouds just because it's going to give me a benefit in the performance. Here's an idea. In this case, I have 5 clouds rather than 4. This is RLNC over here in blue. And this is replication, so I'm keeping uncoded pieces. And what you can see here is the bars, which are the error bars. What these error bars are telling you is, in effect, the variability around the mean. Okay? Now, one of the things is, suppose that I only had 2 clouds. How would you start downloading? Well, you would start downloading from the beginning of the file on one cloud, and you would start downloading from the end of the file on the other cloud, right? And they shall meet in the middle sometime. It's kind of like, when people used to make those railroads, right? Meet somewhere in the middle. The problem, of course, becomes more difficult when, say, I have 3 clouds, 4 clouds, and becomes increasingly more difficult as the number of clouds increases. And in particular, you could imagine with 3 clouds, okay, I have one starting in the middle instead of spreading outwards, one starting at the end, one starting at the beginning. But you would actually wish to know somewhat how fast these clouds are relative to each other to know where to start, right? Maybe actually you want to start the 3rd cloud not exactly in the middle. But these measurements are very difficult to get. Of course, there are plenty of companies that are formed just around getting those measurements, but they're difficult to get and are quite time-varying. So even if you think you got them at the beginning of your download, they will actually change during your download and change considerably. So what you see here is that this is even assuming that I know the measurements fairly well. You have a huge benefit from distributing across the clouds. But this is interesting also for the case of security, because you can see that here what I have is actually I have 32 chunks that I need to recover. So the smallest number of chunks that I can put is 7, right? Because 7 times 5, I have 5 clouds is 35. That's the closest I can get to 32. So even if I keep just this very small portion of the file, in effect, on each cloud, I'm still able to recover very quickly. Here, I'm able to recover, I have 12 chunks per cloud, and you can see the big difference that I get with respect to having, having duplication. Okay, and of course, you have a far less variable download time. Here, I basically have no benefit from keeping everything on every cloud. So at this point, I need 32 chunks to recover everything. I have 24 chunks. I have, in effect, 6 chunks worth of key. I have a key that is 6 chunks worth long, which means that the guessing, and we'll talk about guessing later, would be huge in order to try to recover what's left. Okay? So this is giving me a huge amount of security here without costing me anything from the point of view of performance, right? So I'm still basically getting the optimum performance, certainly much better than with duplication, but with a big security gain. Okay? Now, one of the thing that one has to be careful about, of course, if you're going to be putting your data out there coded, is what happens if somebody pollutes the cloud? So if somebody pollutes the cloud, this could be worrisome. It's not if. I mean, people do pollute clouds, as you know. There are people who make a living just out of, in effect, putting out fake content in peer-to-peer networks to avoid pirating of content. right? So you can make a living that way. There are people who do. And you can imagine that if I'm going to take content, as I showed before, and mix it and re-encode it, right, this could be even more worrisome because this pollution which might have occurred here could spread and could be difficult to counteract. As it turns out, you can do a lot of things here. In particular, you can use codes borrowed from transmission to correct erasures. So you can use codes borrowed from channel codes, in particular things called read-Solomon codes, which many of you know. They're applied in a variety of settings, not just physical layer channel coding, but also storage. They're one of the workhorses of storage. You can do that, in effect, to correct erasures so that you don't care about the fact that even every packet got somehow disturbed. All you really care was the amount of pollution that was put in. And this is really related to subspace codes, which are a very active area of research currently. And actually, I think there's a big European project on the topic. Okay? Something that's particularly nice here is I also no longer need to have a trusted authority. First of all, I have no tracker. I'm not trying to keep track of where the pieces are, right? I mean, you know that, for instance, when BitTorrent was brought down in China, the way that it was done was by bringing down the tracker. There's no tracker, right? So that's it. Nobody can bring you down from the tracker. The other thing that there isn't is there is no trusted authority. Again, if you use something like BitTorrent, you need to take what you received, compute a hash, and verify that that hash is legitimate with a trusted authority. You no longer need to do this. You actually just check internally the consistency. So you're using the fact, remember I told you that we're working over large finite fields. You can actually use, in effect, the discrete log problem, just a Diffie-Hellman approach, to check whether what you said is, that is to say that this is, a particular element in some subspace over some, n-tuple of finite fields, that is exactly what you got. Okay, so you can do that kind of verification just using discrete log. All right. So basically, this is giving you untrusted networks with trusted storage. So as I said, for instance, here I have a large file. I take them into file blocks. I split it. I encode them. I send them all over these different clouds. And if I have here a trusted receiver who has access to 3 clouds, then he can recover the original blocks. But an eavesdropper who may have gained access to 2 clouds but really needed access to 3 clouds because I needed to have, in this case, 6 pieces to recover the whole thing, is not able to recover. Okay? And you can, as I said, make very strong statements about the security of these systems. All right. So if I look more generally at this issue of secrecy, I've talked about eavesdroppers. This is a good time maybe to go back to the canonical issue of secrecy. And what's a canonical issue of secrecy? The canonical issue of secrecy is I have Alice, I have Bob. Alice and Bob are always the nice ones. And Eve, poor thing, always gets stuck in the role of being the mean one. And Alice and Bob are trying to hide their message X from Eve. And of course, if they just send it in the clear, Eve happens to have a channel which allows her to recover it perfectly. So we assume that Eve can hear exactly what Alice and Bob are telling to each other. So Alice and Bob need a separate channel, a secret channel, through which they exchange a key. They then compute a function, which is parameterized by that key k of x. And this function, which therefore gives you a y, which is the function of x, Eve cannot invert. So the point is to make this function difficult to invert if one does not have the k. But if one has the k, as Bob happens to have, then the function can be inverted. Okay. So the idea here is that Eve should learn as little as possible about the message. And the question here when we're looking at these stormy clouds is, how am I going to design this cipher, this k and this f of k? What are the fundamental performance limits? We'll see what I mean by fundamental performance limits. And more interestingly, for our topic of stormy clouds, what's going to happen in the clouds? Okay. So there are different views of secrecy. Probably the cryptographic view is the more popular one, certainly the most widely deployed one. But let's maybe start with Shannon. Obviously, I'm an information theorist. Next year is the 100th birthday of Shannon, as I'm biased. But basically, out of this kind of came a split from his 1949 paper. On the one hand came sort of the information theoretic approach. The other hand came, let's call it broadly, the computer science approach. So we have new directions in cryptography. This is Diffie and Hellman. I mentioned before that in particular you can use their approach to do verification with the trusted authority. The idea here is a complexity view. You have hardness assumptions. You have adversaries that are computationally bounded, right? And that's the way crypto has worked. Now, one of the things that gets you a little nervous about this adversary that's computationally bounded is that, you know, when you have a fair amount of time and when you can farm out a huge amount of computation, the boundedness gets a little uncomfortable. At least for an information theorist, it does. Why does it get uncomfortable for an information theorist? Because we do computationally hard things all the time. All the time, they work. They work in chips. Okay, we can't even tell you where they work. I mean, some of the chips here may have things like low density parity check codes. The decoding of that, we don't know when it ends, but we can make chips, and they work at gigabits per second, and they work every time. Okay, maybe 10 to the minus 9 of the time they don't work. So I cannot guarantee you that it will work, but it does. Okay, so the computational boundedness just doesn't, I mean, obviously this works, right? We know it does. But the computational boundedness does not give you the warm, fuzzy feeling as an information theorist that, you know, that you'd like to have with your secure system. So the different view, and, you know, Diffie and Hellman, very known. This is Aaron Weiner, the late Aaron Weiner, came up with a wiretap channel. The idea here is that at one level you have perfect secrecy, there are no computational assumptions, but instead, you know, you're going to maybe allow a little bit of information to leak. Now, this makes computer scientists really unhappy, just like the computation boundedness makes information theorists feel queasy. This makes information theorists feel very unhappy because they say, well, this makes cryptographers feel unhappy, legitimately so, because what do they say? Well, fine, you only gave me a little bit, you know, 5%, 1%, 0.001% of your rate, but that 0.001% of your rate that you gave me out of, you know, a gigabyte file happened to be the password to my account. That was silly, right? I don't just care about the number of bits. I really need to be able to hide everything. Okay. So, you know, those are some of the things that we struggle with. And here's something where, here's a place where the two sort of come together, okay? And the place where the information theory and the computer science come together somewhat is in this idea of the brute force attacks, okay? So remember the way that we're thinking here, remember the way that we're thinking here of managing these untrusted networks is basically, I'm trying to say that even if you manage to break into 2 of the clouds, if you don't manage to break into all of them, then you're okay. And I have, in order to do that, breaking in, I need to have a cryptographic approach, which is generally controlled by a key, and this key is really the password. Whether it's a key that was generated for you by your computer, whether it's a key that you came up with some, you know, devilishly clever password, either way, that K is the key, and that K is what's protecting that particular cloud. Does that make sense? Okay. And going back to the reason why, you know, the notion of just having a complexity doesn't quite make people so happy is that, you know, many of the attacks that have happened lately haven't been so much in just, you know, computing brute force on f of k. They actually have been at doing brute force guesses of the attacks, right? And this is, if you will, a place where information theory and computer science meet, in the sense that this idea of just guessing and trying to see how much you have to guess in order to break in is one where the two notions meet, okay? So everybody heard about all those embarrassing pictures of different people that were set out. Those were actually brute force attacks. There was nothing where somebody gained access through backdoor or anything. They just kept guessing passwords. And you've all seen many of these password files, and we'll see them in a little bit. But that have been broken into over and over again. And you can see that the distributions are anything but uniform. Okay, we'll talk a bit more about that. Okay, well, you can say, well, I realize that, but okay. Clearly, if somebody guesses my password, it doesn't matter how how clever my f of k was, right? If somebody gives the k away or guesses the k, then we're done. The different ideas for minimum number of bits for security. These are different recommendations. I'll highlight the NIST one because basically this is something where you're having recommendations given that are supposed to last until 2030. That's to say that you can choose this and let it go until 2030. That's a long time. Okay, that's like 15 years from now. And the key sizes here, by the way, are all provided in bits, okay? So one of the problems is that these recommendations assume truly random bits, right? And clearly truly random bits is not what's leading to brute force attacks. One of the questions, of course, is what is entropy? And at this point, you will say, I know what entropy is. It is minus p log p. That's it. I didn't need to come here this morning, wake up early, and battle traffic in order to know what entropy is. Well, bear with me for this cute little XKCD, which actually one of my collaborators, Ken Duffy, brought this one up, and I really like it because, this is sort of how we try to make passwords, right? These clever things where you replace O's with zeros and think that nobody will ever figure it out, and so on and so forth. But if you just look at the entropy, this is of course not a good computation of entropy, this is just a cartoon, but it's not so bad. And you look at this is about 28 bits of entropy, and the difficulty to guess is fairly easy. It takes 3 days at 1,000 guesses per second. Of course, you can do a lot more than 1,000 guesses per second, but remembering that is horrible, right? Which then gets us to everybody goes off and has security questions. We'll talk about security questions in a second. Instead, you could do something like this, correct horse battery staple, which you can remember right away by having some disturbing image of a horse, a staple, a battery, in some order. And the bits here are 44 bits, give or take, so for the same computational power, it gives you 550 years, okay? So one of the things, though, is that people are not even choosing Troubadour. If you look, for instance, at how people are looking at, this is the file of Adobe Passwords, and of course you can download all sorts of systems that allow you to break into passwords, okay, because there are different password files that are out there. Then you see that you have the ciphertext, right? Generally, all of these things have been hashed. But then, of course, so I don't know if you know what happened in the Adobe file. What happened was that they used a single encryption for the entire file, and they left the hints in the clear. So that so of course you have, the silly passwords like 1, 2, 3, 4, 5, 6, and look at the number of users that have this. We're looking at basically 1 million, almost 2 million users that use 1, 2, 3, 4, 5, 6. You can see the indicative hint, 1 to 6 in numeral form, in case there was any way that you were going to do it otherwise. And as such, 1, 2, 3, 4, 5, 6, 9, 0, but not 0. So answer is password, and et cetera, et cetera, et cetera. Okay? So one of the things that happened was that even if you and these were actual ones. That's my secretary down there. I did that to tease him. Even if you had, say, a reasonably difficult password, if somebody had the same password but had a silly hint, then because everything was hashing through a single hash function, somebody could look at somebody else's silly hint, guess their password, and from that guess yours. Right? So in this case, for instance, this user didn't add a security question. He put the phone, but the problem is 6,597 other users chose the same password, and therefore you're able to check it out. So for instance, if you have here, this is the different, different people who had, oops, oh, that's not good. Checking for updates. Could we not check for updates? Yeah. No, just tell them to go. Yeah, yes, use a ladylike language. Yeah, thank you. All right, let's go back to, right. Sorry about that. All right.
Sorry about that.
No, sorry, it's me, yeah. Of course, should have everything updated. And now you all know I don't. All right. Okay. Oops, so here you go. So here's a system where different people put hints, and Yahoo wouldn't necessarily get me to bunny, right? But here we have, pet, furry little bugger, lapin, hop hop. So from these, we can get a feeling that this is probably a bunny. And even though, Tasha, that was not so clear that was a rabbit, right? Not only rabbits are called Tasha, but basically since you had this many users with the same password, even though you may have chosen your password well, you're going to end up with a high likelihood of being broken into. So the attacker is going to say, is the password bunny, and the system says yes or no. Okay. So I told you that, of course, you all think that you know what entropy is. Not that you don't know what entropy is. But of course, there are many different kinds of entropy. And if you look at what we mean by bits in these recommendations by NIST and others, what they mean by bits is entropy, right? Number of bits coming from entropy. So that's compression type entropy. But as it turns out, even though compression, there are very good compressing systems out there, like for instance gzip is very close to optimum. Even though compression is basically getting your system to the case where the number of bits that you have is close to the actual entropy of the system, it doesn't quite give you the right randomization. There's a slight difference there that's important. Regular entropy in particular is not the right determinant when you're guessing. Okay, and this has been known since the 90s, first with the work by Massey, then by the work by Arakan. So basically, if the system is looking at doing this kind of, question, answer, it turns out that the right entropy to look at is not Shannon entropy. It's actually Renyi entropy of order 1/2. The other thing that's a little funny is, and this was just presented, hiding the statistics doesn't help much. Okay, it helps a little bit, but you can actually have a pretty loose description of the statistics, and you can still guess with roughly the same parameters. Now, how does this go when you have multiple cloud systems? Well, now what I'm doing is the attacker, and this is, for instance, what happened with the nudie pictures. What happens is the attacker is looking at a set of different systems, okay, and is attacking several systems until he gains access. Now, of course, if you code it, he will need to gain access not just to one, but to many. So you're making his life harder, okay? But that's basically what he's trying to do. And one of the things that happens as the number of clouds increases, the regular entropy becomes closer to a measure of difficulty. As to say that the order of the Renyi entropy that you're using is starting to become close to the order that corresponds to Shannon entropy. Okay. But it also says that even if you have a lot of them, eventually, you have a limit, and that limit is actually getting to Shannon entropy. The other thing that's funny is if you look here at the guess progress, this is the guess difficulty, is that there isn't necessarily a single worst cloud. So for instance, here, this uniform decrease corresponds to somebody who has a short but truly completely random password. And this guy has a longer but probably user-chosen password. So there isn't a single weaker cloud. There's a cloud that is the most vulnerable at the beginning, okay? And then there's another cloud that picks up being the most vulnerable. So the user-chosen password is the most vulnerable at the beginning because you saw how many people pick 1, 2, 3, 4, 5, 6, right? And all those other silly passwords. But once you got past the silly passwords, it starts getting hard because you have the people picking the horse staple thingamajob, okay? The uniform bits at the beginning are difficult, but then afterwards become the easier one because they're shorter, even though they're random, okay? So one of the things that you can see, and this is something that, again, was not known before that because the approximations actually only gave you the outer curve, not this kink here. The fact is then that now if you have multiple clouds, one of the things that you can start asking yourself is, would I rather have a different password on each cloud, which everybody would tell you, well, of course you shouldn't reuse your password, that's just, bad hygiene. Or would I rather spend a lot of time coming up with a single, dastardly hard password and use it over and over again? And this seems to indicate, don't go off and do it just because I said so, but the math currently seems to indicate that actually the latter is better than the former. Right. That, you would actually have been better off with that one really nasty, nasty, nasty password. There are prefactors there, so don't, again, be careful. But, these are highly unintuitive sort of things. Okay. Now, for the last 15 minutes of the talk, we've been talking about the Stormy Clouds, and I think, what I've told you is, I'm hoping sort of combination of good news and bad news. So the good news is, you don't need to have crypto, you don't need to trust Tor, you can just use coding to give you a lot of security that otherwise you wouldn't have. You do need to be careful about guessing, because any time that you're going to have any sort of encryption, it may no longer be so much a question of just breaking the encryption as actually just guessing your password, okay? But the last thing that I want to talk about, which is another thing people are quite concerned about with having more and more data in the cloud, is the issue of, in effect, inference. It's an issue of inference, which is, for instance, how do you keep data secure when you're doing not just from breaking in, but just from the fact that people can infer, in effect, by observing things that they had access to legitimately, not because they broke in your password. Okay, so a lot of this has been around health use. Of course, we all know why it's very useful to have big data. This is something that I had an interesting little story in the U.S. It made some amount of turmoil in the news because a teenage girl was doing searches and Target sent her coupons for baby products. The father of the girl went to Target, absolutely livid, saying, "How dare you send these things to my daughter?" And a couple months later went and apologized because indeed she was pregnant. So basically, just from looking at the searches, Target was able to figure out the state of the girl before the father was. And this was actually highlighted by President Obama this very year. This idea that you want to have the personalized information, but that the protection of the information, particularly the privacy, not just not just some subset of the information is very important. So here's an example. This is an available database, okay, and this available database comes from a hospital, right? So we didn't hack anything. Okay, you can get it too. And basically, you can see the number of patients here. This is the size of the circle. Pink is for women, blue is for men. And these are the different age ranges. And this comes from the US, so they keep track of ethnic categories. So you can see here is that if you're between 0 and 10 and happen to be Asian and a girl, your chances that somebody will be able to find who you are by correlating with this are pretty high, right? As opposed to, for instance, if you're Caucasian between 70 and 80 and male. Okay, these are actually diabetes patients. So, you know, that explains sort of the fact that it tends to be an older demographic. So one of the questions here is how much can they find out? So remember when we had Bob, Alice, and Eve, the classical setup, right? Eve could see everything that was sent, and so you had to hide it by encrypting it. All right. Now this is a little different. We have a channel, but the channel is not a direct channel. It's not just the usual that, you know, the Eve is actually the eavesdropper. She's actually listening in. You have the private information, and it's somehow, you know, think of this as not a real channel, but just some sort of correlation, be sent into the public information. And Eve is trying to make an estimate. So she gets to see the public information, or at least some subset thereof, okay? And there's some connection here. All right. So this is the private information, X. The public information, which is what Eve sees, is Y. So you still have Eve seeing Y, X being what actually is being hidden. And you have some probability of error, you hope, which is the probability that X is different than X hat. Okay, so that Eve is not able, from whatever best estimate she can create, to figure out what happened. Okay, so how do people usually deal with this? Well, one of the best known approaches, which was due by Sweeney from Harvard, is K-anonymity. So basically, you're clustering entries together to hide in the crowd. That is to say that, remember, the problem here was that this patient, because of, you know, her demographic, didn't have the same level of anonymity as a patient in here. Okay, so patients should not have different anonymity because of the demographic. So, like I said here, certain attributes may uniquely identify a patient. This is basically the table that whose characteristics I showed you before with those circles. Okay. So guaranteeing anonymity, one of the things we can do is actually here we can, again, use coding techniques. And one of the ways we can use coding techniques is, as much as I told you that coding for compression is not going to do it for guesswork, just for getting uniformly distributed passwords, it actually turns out, that you can do quite a bit here in the sense that you can map code words to attributes, and that the simple use of things such as Hamming codes, very, very simple use of actually in this case, sorry, Huffman codes. The simple use of Huffman codes can actually get you a lot of anonymity. But, you know, sometimes when people are finding things out, it's not necessarily because they went to this database, right, and they try to infer from this database who you are. Very often, the correlation between the X and the Y can be pretty murky. Okay, and then the question is again, what can they find out? And how can I make sure that the probability of Eve inferring X correctly is low? Okay, so how do people do this? So for instance, let's go back to the question of the girl and doing her searches on the web and Target figuring out that she was pregnant. Basically using machine learning techniques, okay? And techniques have been developed since the 80s. And one of the main workhorses, at least on the theoretical side, much of what happens in machine learning, as you know better than I, tends to be fairly heuristic, quite powerful, but very heuristic, actually is based on principal inertia components and correspondence analysis. This goes back to the 40s, and even before in the 30s in Gebelen. So if you look at the history, things were going great. Then the Second World War, you know, disaster for a lot of people, including correspondence analysis, and then kind of picks back up after the war. Between what is observed and what is not observed, okay? And the question is, people have been using, and, you know, again, there's a massive literature, but probably, I would say, Greenacre is sort of the most well-known combination going from correspondence analysis to the kinds of techniques that we would think of as machine learning, sort of taking things that were coming from one end of statistics and making them more usable algorithmically. these have been used to infer information. But if you're an information theorist, one of the things that we like to do is we like to have converses. And converses are, this is what you cannot do. This is the limit you cannot beat, right? So for instance, you look at capacity, there's a forward theorem saying, I can do this well, I can get this much data through reliably. And there's a converse which says, saying, and you can do no better. And the converse, interestingly, is actually based on something which now we would probably call statistics rather than information theory, right? Which is called Fano's lemma. So the question is, can I tell you in an information theoretic style what people cannot find out? All right. So the problem here is going to be, to some extent, how do I say something about this estimation error, given that I don't even have enough data telling me how X and Y are related? In the other questions, for instance, the crypto question, I knew exactly how they were related. Right? There was that F sub K. You give me K, I know F. Right? So of course, Eve doesn't know K, but I, who I'm doing, the omniscient information theorist, that sounds like a contradiction, but the person who's doing the analysis knows exactly how that function is created. In this case, I may not even know how this relation between X and Y, between the private information and the public information is happening, particularly because it's murky. I don't even quite know what public information is available, and it changes in time. Right? So any analysis that requires exact knowledge of the relation between X and Y in the way that we had exact knowledge in the case of crypto is simply not going to hold. Okay. So what happens is that it turns out that even when the relation within a private and public is unknown, or actually very lightly known, we can say something about not just protecting X, but protecting certain functions of X. That is to say that I may not want to know all of your private information, but I may want to know some subset of this. And this is the most math I'll show you, because we shouldn't do that in the morning. Okay? But it turns out you can give a lower bound on the probability of error. So remember that M is the cardinality of X. Okay? That's how many possibilities there were for X. Okay? So basically, if I take a random guess, uniform guess, my probability of guessing X is 1 over M. Okay, so if I had no information from looking at Y, it would be lower bound of 1 over 1 over M, right? That's just if I have no clue and I try something at random. And this is how much more I'm gaining as an attacker from having looked at Y. And, if M is large, this is square root of M minus 1 over square root of M. It's not big. But the thing here is this chi-squared. This chi-squared is actually the sum of the inertia components. And this is the sum of the inertia components of the correlation matrix between X and Y. And I may not know it exactly, right? But it's just like you don't exactly know the shape of a funny-looking rock. But you can say something about its moments of inertia, right? It's going to first go this way, and then it's got another one that way, right? You can say something about moments of inertia physically. So this is actually a very physical interpretation of data. Okay. The last thing I'm going to do in the last few minutes, just because we started a little late, is talk a bit about security questions. Remember, we talked about security questions. And one of the things that happens is, because we try to get those troubadour-looking things that are very hard to remember but easy to guess, is we give ourselves security questions. You may remember that Sarah Palin's email was hacked because some kid went out there and figured out in the public domain things like, where she had gone to high school, Vasilisa, and everybody knew this. Okay. And so there's a lot of issues here. For instance, Facebook security questions, how easy it is to hack somebody iCloud with the security questions. There's a lot of evidence, particularly coming out of the last year or so, last year, 2 years, that it's much easier to hack security questions than passwords. Okay. And remember that even that was the Achilles heel also in that password file. right, was that security questions were really clear, and somebody else's security questions were giving at the fact that my password was bunny. Okay. So the question is, can I make hard questions? Right? Can I come up with questions that are going to be hard to guess? So design the questions so that the growing data is now allowing you more chances to hide. So usually you think, well, the more publicly available data there is, the more likely I am to be found out. Right? But also, if there's more publicly available data, there's more chance to dither in there for my security question. So the goal here is to produce a non-trivial function of information that is as uncorrelated as possible with a function that can be produced based on somebody else's information on the public. So that the public and the private, even though they're correlated, and we may not know exactly how they're correlated, we still only have this kind of vague feeling of how they're correlated using just the sum of inertia components, but basically using the same sorts of techniques, we can find out how to find difficult security questions. This means, by the way, that more observations, that somebody having, that if the attacker has more publicly available information, we can actually have better secrecy if used properly, which is completely counterintuitive. Okay. So because we started a little late, I'm not going to do this. And instead, I will just talk a little bit about conclusions. So we talked about Stormy Clouds, big data, data analytic, passwords. You know, the question is, what can we do? It's a rapidly evolving domain full of counterintuitive results. My belief, and I hope I illustrated the reason for this belief, is that the use of coding and information theoretic approaches, not necessarily in the more classical information theoretic sense, but certainly in the broadly understood information theoretic sense, which is looking at lower bounds for converses, and looking also at the active use of the algebraic nature of data for coding, is really going to provide new approaches, and that we really should be using information theory. And with this, I'll stop and take questions.